Hi, my name is Rodrigo Cedillo, and today I'm going to present you my argumentative exam of the subject of modeling of electromagnetic system in engineering. So I'm going to show you the question and then I'm going to show you my procedures. Okay, for the first situation we have a magnetic field due to a current carrying wire and a square loop. And for the part A, we have a straight filament using a Biot-Savart law. And for the part B, we have a magnetic field from a square current loop at the point P0, 0, theta 0. So for the part A, we did this. We have our Biot-Savart law here. We have our point in the source of current, that is this one. We have the separation vector from source to the test point. We have our test point and the perpendicular distance from source to the observer. So as I said, I use the Biot-Savart law to find the magnetic field created by a long straight wire with a constant current. Then I divide for 4p and I multiply by the integral of dl cross r hat over r squared. Then I define all the vectors involved, the differential length vector dl and the vector r that points from the wire to the observation point. I draw the triangles to help me to define the geometry. Here we have to get alpha 1, and here we have to get the c squared multiplying c times c. And we obtain this, that applying to the cosine alpha 2 we get this. And that's all for part A. Then for part B, as the exercise says, it's a square loop, so it has 4 segments. This is the first one. So in this part B, I apply that result to a square current loop lying in the xy plane. I calculate the magnetic field at a point directly above the center of the loop at a certain height on the theta axis. Then I analyze the first segment one by one, like this. This is my first segment and I get this. This is my second segment and I get this. And this is my third segment and I get this. And for my fourth segment I get this. So for each side, as we see, I identify the direction of vector of the current, the position vector to the observation point, and then I use the same Biot-Savart formula to calculate the magnetic field. I compute the cross product and the magnitude of R, and after that I just add the 4 results together. And that's all for part B. Let's go to the situation 2. So for the situation 2, we have a magnetic field due to a circular loop in the x theta plane. We have to apply the Biot-Savart law as 2, and we have to evaluate the integral and use diagrams, and that's all. So this is what I did for situation 2. We have our Biot-Savart law again, and we have our 2 diagrams from a top view. We have also our unit vector direction. So in this situation, I basically analyze the magnetic field produced by the circular loop in the x theta plane. I center at the origin and with the clockwise current flow when viewed from the positive y axis. Then I calculate the magnetic field at 2 symmetric points, one above and one below the loop along the y-axis. Here we have our direction of the magnetic at the up vector, and here we have our direction of the magnetic at the down vector. Horizontal components cancel each other due to the symmetry, which means we cancel this one. Then mathematically the expression is computed as this, and this needs to be empty. And with this result, might lead us to think that Biot-Savart was wrong. So to get the direction of the magnetic field, we get dl times r. And here we have our diagram that horizontal components cancel once again due to the symmetry. After simplifying the integral, I evaluated from 0 to 2p, and the final result showed that the magnetic field at each point has only a vertical component along the AJ direction. Also, we get that for the point at negative J0, the field points up, and for the point located at positive J0, the field points down. And that's all for our second situation. Let's go for the third one. So our third situation is a magnetic field due to an infinite current sheet, and we have to use our Ampere's law. As I previously said, we use our Ampere law, we apply symmetry and field direction, we compute the line integral, and we discuss the physical interpretation. So here is our situation 3. In this question, I analyze the magnetic field created by an infinite current sheet lying in the gz plane, and the sheet carries a uniform surface current density flowing in a negative zeta direction. For this, using the Ampere's law, I choose a rectangular Amperian loop symmetric with respect to the sheet. Due to the second nature of the sheet, the current density is this one. Based on symmetry, we are assuming that plate is made of infinite number of wires. Then we do our analysis of wire on 0G0 and 0 minus G0. And vertical components cancel due to the symmetry. For our first wire we obtain this, and for our second wire we obtain this. So here we have our wire in 0 G0 with our diagram, and here we have our wire of 0 minus G0 with our diagram too. Obtaining that, we do the calculation of our H, and we do our 4 segments, and this is the final result. This confirms the result expected for an infinite current sheet. The magnetic field is constant in magnitude and direction on each side, and change seen across the sheet. So that's all for the third problem. We are going to go to the situation 4. Okay, in the situation 4, we have a motion of a charged particle in a magnetic field. We have to apply the Lorentz force law. We have to analyze the trajectory, to do a graphical representation, and to discuss the periodicity. Okay, so this is what I did for situation 4. We have here our Lorentz force law, and we cancel the E because it's no electric. Then we do our function of velocity of the particle with respect to time, and then we set up of Newton's second law. Then we do our system of differential equations of Bx, By, and Bzeta. We know that Ba is constant, and then we substitute, and from tables the solution is as follows. Then we do our expressions of velocity and our expression of position. So with both